Okay, calculus students, we are ready now for our third lesson in chapter 11. In 11.1, we discussed limits, and we saw how limits helped us determine whether or not a function was continuous at a particular x value by introducing the three-step test for continuity that was based on limits. And now we will talk about how limits work into the idea that we've also studied before called a rate of change. A rate of change is not a new term. You've heard that term before. A rate of change is the same thing as slope. And we've talked about slope in probably every algebra class that you've ever had. Slope is the change in the values of y compared to the change in the values of x. And a great many times we write slope, there is a formula for it, and we've oftentimes use that formula as y1 minus y2 over x1 minus x2. But in the interest of being lazy, mathematicians are lazy people after all, believe it or not. And so they do a little shorthand called delta y over delta x. And that little triangle is the Greek letter delta, and it means difference. So what this terminology means is the difference in the values of y based upon the difference in the values of x. And in the case of linear functions, which we've again talked about before, y is equal to m times x plus b is a linear function. And the value of m was what we call the slope of the function. And what that value of m did was it made a change in the value of x by multiplying times x. Sometimes we would refer to division, but it actually could be multiplication or division. And then that resulting change in x caused a change in the value of y. And in linear functions, m was a constant value. Meaning that it was a single number and it never changed. If it was 1/3, it would always be y would change by 1 unit as x changed by 3. If it was 4, then it means that y changed by 4 units if x changed by 1. So this was all linear functions. However, other functions also have slope. In fact, all functions have slope, meaning that they have a rate of change. As the x values change, the y values also change. The difference is that in nonlinear functions, the rate of change is not constant. That rate of change will change over time. And And it will change still, just as it did in linear functions. It will change the value of y based upon what was done to x, but x tells you what you're doing to that function, or the equation tells you what you're doing to x in that function. So to kind of get started with an idea of how this is going to work, let's suppose that we take a trip from Nashville and we're driving east. And every half hour, we're going to make a note of how far we've driven. How far have we traveled? And for the first 3 hours, we have this table of values down here. And we see in this table of values that at time 0, in other words, n of 0, we have gone 0 hours. And that simply means, of course, that we're still sitting in the parking lot. But then by the time we have driven for 1 hour, we see that we have gone 55 miles. So n of 1 is 55. And we see that n of 2.5 is 124 miles. And the question then is, what was the distance traveled during the second hour? Now, the second hour was actually the distance traveled from the first hour and the second hour. And so the actual distance was 124 minus 55. I'm sorry. Back that up. Looking at the wrong thing. During the second hour. During the second hour, we're looking at the distance traveled from 1 to 2 hours. There is your second hour. And then we see that that actual distance is 104, which is how far we'd gone at the end of hour 2, minus 55, which is the distance that we had gone at the end of the first hour. And 104 minus 55, I believe, is 49 miles. And because that 49 miles was traveled in the value of 1 hour, or the time of 1 hour, because that was hour 2 minus hour 1, which gives us 1, then we know that our average speed was 49 miles per hour. And that central word, per, that's important because that's what tells us that it's a slope or a rate of change. It's a change in the miles divided by the change in the hour, or the change in time. At a half an hour, we had traveled 30 miles. And at an hour, we had gone 55 miles. We had gone 80 miles in that 1.5 hour. I'm sorry, 49 miles per hour. Because we were going from 1 to 2, so that was 104 minus 55. 55 miles an hour after, or 55 miles after 1 hour, 138 miles after 3 hours. The question, and we know that distance is equal to rate times time, and because we know that, since the rate here we also refer to as speed, then we know that the average speed is distance divided by time. So the average speed of the whole trip would have been, since we are recording for 3 hours, it would be n of 3 minus n of 0 divided by 3 minus 0. And since at the end of 3 hours we had traveled 138 miles, and we had been traveling for 3 hours, that gives us the average speed of 46 miles per hour. We can actually use this approach to determine the average speed for any time interval on the trip. Hour divided by 1 hour. And all we're doing is finding slope. Slope is your average rate of change. It's the slope between 2 points, the first point being a half an hour and the second point being an hour. So going back and looking at our table, so 55 miles minus 30 miles divided by the actual time increment here from 1/2 to 1 hour is 1/2 hour. And 55 minus 30 is 25. And 25 divided by 0.5 is equal to 50 miles an hour. And from a half an hour to 1.5 hours, returning again, minus the 30 miles from the half hour. And this is a time difference of 1 hour. So 80 minus 30 is 50 divided by 1, which again gives us 50 miles per hour. And we've already seen from 1 hour to 2 hours that our average speed was 55 miles, which gave us the 49 miles per hour. And from 1 hour to 3, the end of the trip, and that would be 2 hours. Would be a total of 83 miles over 2 hours, which would be 41.5 miles per hour. But you see, in every case, regardless of what the times were, what we did was we actually took B, the end of the time, minus A, the beginning of where we took the time, and we used the distance at time B minus the distance at time A, and that gave us the average speed. Okay? And keep in mind we're talking average speed, which is the same as a slope, and in order to find slope you have to have 2 points. In this case, 2 different distances. Back to this slide, the average rate of change over an interval of time. But we don't know what the exact rate of travel was or the speed was at the end of the first hour, because from the beginning of time at time equals 0 to the end of the first hour only gave us an average, and during the time from when we started the trip until we'd traveled for 1 hour, you have to consider that we sped up, we slowed down, probably stopped for traffic lights, and so that rate of change was never constant. It was always varying at 2 different points in time. So this gives us the definition of the average rate of change. The average rate of change from point A to point B is the distance that you traveled at point B minus the distance you traveled at the end of point of time A over the actual change in the time, and that's called the average rate of change. And if you look, you see that the average rate of change is, in fact, the same as slope. It's like a slope formula. And when we talk about average rate of change, I'm going to abbreviate that as AROC, average rate of change. And the reason I'm going to abbreviate it that way is because in a few minutes we're also going to talk about the instantaneous rate of change. And what that's going to be construed as is going to be the slope or the rate of change at one single point. So thinking about distance, we can figure out the average rate of change. So what I've done here is we have a graph that shows for our time in our original problem the various distances that we had traveled. For example, here this is the first half hour, and that's where we had traveled 1/2 hour, and at that time we had traveled 25 miles. And at the end of the first hour, we see that we had traveled 30 miles an hour here. And by the time we got to the end of the first hour, we had traveled 55 miles. And so we see that 55 minus 30 gave us 25, and the change in the time was 1/2 hour. And that was what gave us our average speed of 50 miles per hour. And we could use these points along this graph and calculate any average rate of travel that we wanted to. But trying to find the average rate of travel at exactly 2.5 hours, for example, that would not be as simple, because you see that the function isn't actually straight, it's actually changing throughout time. So in this figure, we're going to look at something that the change is a little more pronounced. This figure shows that the total average amount appropriated annually in billions of dollars by the U.S. Department of Education shows how this amount has changed in recent years. So what we want to find the average rate of change per year in the Department of Education appropriation from 2009 until 2013. So we see here that in 2009, the appropriation was $63.52 billion. And in 2013, it was $65.70 billion. And so in order to calculate that change, what we're actually going to do is we're going to try to connect up those 2 points with a straight line. And so over the distance of four years, because 2013 minus 2009 is 4 years, we see that the appropriations have gone from 63.52 in 2009 and 65.70 billion in 2013. And so using a calculator, we will calculate the difference. And we see that the difference in the appropriations is $2.18 billion divided by 4 years tells us that the rate of change, the average rate of change, remember, is $0.545 billion per year. And so here is our calculations. Once again, this is a slope. This is y2 minus y1 over x2 minus x1, or the change in appropriations divided by the change in time. And the way that we interpret that, and throughout this, interpretation is going to be very important, so you want to be sure that you always interpret your answer. The interpretation of that is that on the average, the amount appropriated went up by $0.545 billion, which is $545 million per year during the years between 2009 and 2013. So thinking about only that, we're only looking at those 2 points. But does that tell you very much really about what happened between 2009 and 2013 to those appropriations? And I think no, it actually doesn't. That was probably pretty close to the same rate of change for the first year, but then notice in 2010 to 2011, we had a huge increase. And then from 2011 to 2012, it dropped down a little bit. And then from 2012 to 2013, it dropped way back down, close to what it actually was comparatively in 2009. So some big changes that weren't accounted for just by talking about the average rate of change. In fact, if we look at the rate of change from 2011 to 2013, we're looking at an entirely different rate of change, and that would present us with an entirely different picture. Because then we would use only the points 11, 68.35, and 13, 65.70. And so that rate of change would be 65.70 minus 68.35, and that would be divided by 2011 to 2013 is a time of 2 years. And that's 2.65. And notice that's negative 2.65 over 2 years. And so our average rate of change between those 2 years now is negative 1.325 billion. And that's $1 billion per year. A very, very different amount if we looked at the entire interval. A very different rate of change. So in the next example, we're going to return to talking about the distance that a car travels. This time we're going to talk about something a little different from what we started out talking about. Now we're going to talk about the instantaneous rate of change at a particular point in time. So suppose that we have a car that stopped at a traffic light, and when the light turns green, the car begins to move. And so when that car begins to move, it starts out slow, but as you press on the gas, then its speed increases. And we're going to assume that the distance traveled by the car is given by this function, which you notice is not a linear function. S of t is equal to 3 times t squared for the time interval for the first 15 seconds. Only the first 15 seconds. Now, we could find the average speed of the car over that 15-second interval. The average speed would be easy to figure out. We would simply take the difference of 0 at time 0, because the car's still sitting still, and then we would take 3 times 15 squared and get 675. So 675 feet, because this would have to be measured in feet since we're talking in a matter of seconds, would be 675 feet divided by 15 seconds would give us an average of 45 feet per second. So if we're talking about average, then that's 45 feet per second. But what we actually are interested in at this point is, what if we actually wanted to know the speed at exactly 10 seconds? That's an entirely different scenario. That's what we mean by instantaneous rate of change at 10 seconds. Now, it would be easy to find out how far we've gone at 10 seconds. Because how far we've gone would just simply be S of 10, and that would be 3 times 10 squared, which would be 300. We would have gone 300 feet at exactly 10 seconds, but that doesn't tell us exactly how fast we're going at 10 seconds. So at this point, we're ready to talk about an entirely new concept, and that new concept is referred to as the instantaneous rate of change. And in order to explore this idea, we're going to use the idea of limits that we discussed previously. And what we're actually going to do here with the part about the limits is we are going to approach 10 seconds, which is the point in time we want to find the speed at, by first going for the interval, the average rate of change, for the first tenth of a second, and then for the first hundredth of a second, and then for the first thousandth of a second, and see what happens as we do this. So what we're doing is we're actually letting the change in time is approaching 0. And the way that we're going to do this is we're going to go to our y equals menu, to y1. We're going to enter the function for the car's distance traveled at any particular point in time, t. And in this case, we're going to have to use x in place of t. And the formula was 3 times the time squared. So that's going to be in y1. And then from there, we're going to look at the table with your table set up to let us ask for for particular values. So we already know that y1, or S of 10, is 300. So looking at t equals 10 for all of these, we know that value is going to be 300. But for 10.1, 10.01, and 10.001, we're going to get different values. And as a matter of fact, for 10.1, the distance that we traveled is 306.03. And for 10.01, it's 300.6. And for 10.001, it's 300.06. And of course, for the increment on all of these, it's going to be the difference between 10 and 10.1. So for the first one, it's going to be 0.01. Excuse me, 0.1. For the second one, it's going to be 0.01. And for the third one, it's going to be 0.001. And each time, in the numerator, we're going to be subtracting the initial time, which is at 10 seconds, which is your 300. And so we're going to see what happens. So as the time interval gets closer and closer to 0, starting out at 1/10 of a second, we have gone 6.03 feet. In 1/10 of a second, which is 60.3 feet per second. And these all are going to be feet per second. And then 300 subtracted from 300.6 is 0.6 feet in 1/100th of a second, which is 60 feet per second. Exactly. And for 300.06 minus 300, that's 0.06 feet in 1/1000th of a second, which is 60 feet per second. And so what we see an interpretation here is as the time interval approaches 0, the speed approaches 60 feet per second. And so that means that the instantaneous rate of change at 10 seconds, the car is traveling at 60 feet per second. So just to summarize, the results that we've just gone through suggest that the exact speed at 10 seconds is 60 feet per second. And the way that we're actually going to do this, or confirm this, is using the idea of limits. Get this to where we can read it a little bit better. We're going from t equals 10 seconds to t equals 10 plus h seconds, where h is small, very, very small, but not 0. And h represents a small change in time. So remember, what we're actually doing here is we're going to take 10 plus h and plug it into the function, and then take 10 and plug it into the function, and that will give us s of 10 plus h minus s of 10 over 10 plus h minus 10, and that's going to give us 3 times 10 plus h squared minus 3 times 10 squared over 10 plus h minus 10. And of course you realize that 10 plus h minus 10 means those 10s just drop out, and that leaves us with h. And when you square 10 plus h, what you actually get, and this is very important, you need to remember this, when you square 10 plus h, you don't get 10 squared plus h squared. That is actually 10 plus h times 10 plus h. And so 10 times 10 is 100, plus 10h is plus 20h, and then h times h is h squared. So 10 plus h quantity squared is 100 plus 20h plus h squared, and when we multiply that by 300, by 3, we get 300 plus 6h plus 3h squared. And then, of course, 3 times 10 squared is 3 times 100, which is 300. So when we combine like terms here, then 300 and 300 cancel each other out, which leaves us with 60h plus 3h squared over h, which is what we have at this step. And if we factor out an h in front, then while we're trying to let h approach 0, we can't do it in this expression, but when we cancel out the h's, we wind up with this expression. And when h then is very, very small, or as h approaches but is not necessarily equal to 0, that actually equals 60 feet per second. This is the algebraic method of taking the instantaneous rate of change. So in summary form here, the instantaneous rate of change at t equals 10 is given by this limit. The limit as h approaches 0 of s of 10 plus h minus s of 10 over h, which we see that the limit as h approaches 0 of this quantity is the limit as h approaches 0 of 60 plus 3h, and as h approaches 0, it shrinks up and virtually disappears, and we come out with 60 feet per second. And that gives us our instantaneous rate of change formula. And it gives you the instantaneous rate of change formula for any value of x equals a of this quotient, this limit of this quotient, provided that limit exists. Because remember, that limit has to exist. As we approach from the right and the left, that has to actually exist. Now, a couple of big cautions here. These are both very important. First of all, remember that f of x plus h does not equal f of x plus f of h. To find f of x plus h, you replace x with x plus h in the original expression. So, for example, if f of x equals x squared, then f of x plus h is x plus h squared. And keep in mind that not only did f of x plus h not equal f of x plus f of h, it also does not equal x squared plus h squared. Because when you square x plus h, you are actually saying x plus h times x plus h. You will have a middle term. That is very, very important. So what we're actually doing in this case is we are using the idea of a secant line. A secant line is a line that cuts through a function in two different points. And by sliding those 2 points closer and closer and closer together, which is what we were doing in the last slide, we are having that actually approach what's called a tangent line. So we're trying to move in this case we're treating 15 as t plus h. Only we're letting h approach 0. So we're going from 15 to maybe here, and then here, and then here, and then here, and then here, until finally that point is coming so close that 10, s of 10, and 10 plus h, s of 10 plus h, are so close together that they're practically on top of each other. And for the rest of our problem, we're going to talk about an example in manufacturing, because this is, after all, a business calculus course, and we need to see how this is going to be used. So we're going to look at this application problem. Company determines that the cost in dollars to manufacture X cases of the DVD, mathematicians call it an embarrassing moments, is given by this cost function. And this is a cost function. And notice here that we do have a fixed cost. Some things never change. This is our fixed cost. But in this case, our marginal cost, we're dealing with both a linear factor and a quadratic factor. And notice also that this is only good for the interval from 0 to 7. And 0 to 7 is the number of cases. And the first thing they want us to do is find the average change per case in the total cost if the number of cases manufactured changes from 1 to 5. Second thing we want to do is to find the additional cost when production goes from 1 to 2 cases. And then we want to find the instantaneous rate of change in cost with respect to the number of cases produced when just 1 case is produced. So the first thing that we'll talk about is the average cost per case. And the average cost per case from 1 to 5 is going to be the cost of 5 minus the cost of 1. And 5 minus 1 is going to be 4 cases. So the average cost of 5, or the cost of 5, I'm sorry, just use your calculator, is going to be 100 plus 15 times 5 minus 5 squared. And that's 150. And the cost of 1 case is 114. And so if I take 150 minus 114, I get 36. And the average of that $36 spread over 4 cases is $9 per case. And so the correct statement for your conclusion says the average cost per case and the total cost of if the number of cases manufactured changes from 1 to 5 is $9 per case. And notice that verb tense, it is that much. It would be okay to say it is that much or it was that much. So then we move to the second part of the question. Find the additional cost when just one more case is produced, going from 1 to 2. Well, the cost of 2 cases is $126. And the cost of 1 case, if you recall, was $114. And that's a difference of $12. And the reason that we're not making this into an average rate of change, although we could, is because the difference here was only 1 case. And so that's $12 per 1 case. And in either case, that's the additional cost when production is increased from 1 to 2 cases is $12. But now we move to the part where we're talking about an instantaneous rate of change. Find the instantaneous rate of change in cost with respect to the number of cases produced when just 1 case is produced. That means we're doing the cost of x plus h, where h is very small, minus the cost of x, and x in this case is equal to 1. So what we're going to do is we're going to take this cost function, and first we're going to plug in x plus h everywhere that you see x. And so that's going to give us 100 plus 15x plus 15h minus x squared plus 2 times x times h plus h squared. And then in order to eliminate the parentheses, I'm simply going to change the signs inside the parentheses to all negatives. And eliminate the parenthesis. And so the result is going to be this whole big expression, and notice that none of these terms can be combined. But then from that expression, I am going to subtract c of x, which is this function here. So when I subtract that, I'm going to subtract 100. I'm going to subtract 15x. And I'm going to subtract negative x squared, which becomes positive x squared. And so what happens in the end result of that is that the 100s drop out, the 15x drops out, and the x squared drops out, and it leaves me with (15h) minus 2xh minus h squared. And that's all going to be over h. So now that we have this, we can take 15h minus 2xh minus h squared and when we put that over h, since we're going to want to let h approach 0, it actually is simpler if we would factor out the h and get rid of that denominator. And so at this point, we actually have a formula for any value of x where we can let h actually approach 0. Just for the practice, on the next page, we're actually going to plug in x equals 1 rather than using just x throughout. 100 plus 15x minus x squared. So, kind of repeating what we've just done with x equals 1, c of 1 plus h minus c of 1. If you recall, the cost of one case was $114. So just keep that in mind. C of 1 plus h is going to be our cost function. And that's all going to be minus 114. And that's all going to be divided by h, but I'm going to try to simplify it before I go there. So this simplifies to 100 plus 15 times 1 is 15, and 15 times h is 15h, minus 1 times 1 is 1, plus 2h, plus h squared. But remember, this is what's in the parentheses squared, and I'm subtracting that. So again, that's going to be minus 1 but it's also going to be minus 2h and it's also going to be minus h squared. And so when I simplify this, what I'm actually going to have is 100 plus 15 is 115, minus 1 is 114, and at the end I've got this minus 114. So 114 minus 114 is going to be 0, and all of that will disappear, which will leave me with 15h minus 2h minus h squared, all divided by h. And as we saw before, if you factor out that h, that'll get rid of that h, and that h, and take one of those away. And then that h will cancel that out. And you'll wind up with 15 minus 2 minus h. And as h approaches 0, we get 13. And the interpretation of that, then, is when just one case is produced, the cost is increasing by $13 per case. That didn't belong there. But the thing I want you to pay attention to here the most is the change in the verb tense. An instantaneous rate of change is always either present perfect or past perfect tense. You have the ing. It either increased or decreased if it's an average rate of change. But if it's an instantaneous rate of change, it is increasing or is decreasing or was increasing or was decreasing. You have the additional words that you have to have in there, and that's very, very important language distinction to make it clear what you're talking about. So at this point, we have your term 4, which is your chance to do a problem. And you should stop here. If the cost function is given by c of x equals x squared minus 2x plus 12, find the instantaneous rate of change when x is equal to 4. So you should try that and then check your answer either in the e-text or in the answers that I'll provide to you. So pause the recording and do the your turn problem and make sure you understand the process. So for the last part of our lesson, we're really talking about some definitions here. And we're actually redefining some things more than anything else. We define the marginal cost as the instantaneous rate of change of the cost function. It's the instantaneous rate because we're talking about the rate of change at a particular value of x. If that cost function were linear, then that instantaneous rate of change is constant. It has a constant rate of change in the form of m. But if it's a nonlinear function, we have to use the four-step process that we just looked at in order to figure out what the instantaneous rate of change is. Marginal revenue is defined similarly as the instantaneous rate of change of the revenue function, and marginal profit is defined as the instantaneous rate of change of the profit. And one caution that I want to bring forth here is that you need to remember, when we're talking about profit, profit is always your revenue minus your cost. So even if the profit function isn't given to you, if you have the revenue and the cost function, you can find the profit function. So our problem here, we are to find the instantaneous rate of change in the cost when 5 cases are made. So what that means is we need to know, first of all, let's just go ahead and define the cost of 5 cases. Because that's going to be a constant, and there's no need to fiddle with algebra for that. So the cost of 5 cases is $150. So we know that up front. Now we need to find the cost of 5 plus h. And that's going to be 100 plus 15 times 5 is 75. And 15 times h is 15h minus 5 squared is 25 plus 10h plus h squared, and then as before, that's going to be 100 plus 75h plus 15h, I'm sorry, not 75h, let me take that out. Minus 25 minus 10h minus h squared, and then from all of that we're going to subtract 150 for the cost of 5 cases. And then we're going to divide all this by h, but we'll simplify before we do any division. 100 plus 75 is 175, minus 25 is 150, and 150 minus 150 is 0. And that leaves us then with 15h minus 10h minus h squared. And 15h minus 10h is 5h minus h squared. And if I factor out that h, and then I divide by h, then what I have is my cost function. my marginal cost function. The limit as h approaches 0 of 5 minus h is equal to 5, and that's going to be $5 per case. And once again, the correct explanation of that is when 5 cases are manufactured, the cost per case is increasing by $5 per case. Or if you had a past tense situation, when 5 cases were manufactured, the cost per case was increasing by $5 per case. So this is just a restatement of what we just said. When 5 cases are manufactured, the cost is increasing at the rate of $5 per case, but notice that as the number of items produced increases, the marginal cost decreases, which you might expect, because the reason that happens is that if the cost of making the first item bears all of the fixed cost, but the cost of making the third item splits the fixed cost among 3 items, and the cost of making 5 items splits the fixed cost over 5 items, and the cost of making 7 items splits the fixed cost over 7 items. So the amount of fixed cost added to each case becomes smaller and smaller, and that means that as your number of items produced increases, your marginal cost is going to actually decrease, because you're talking about marginal cost as your rate of change of cost. That's the rate of change of the total cost. So at this point, you should be ready to work on your homework, and let me know if you have any questions.